Hello, welcome to our Latin America webinar on physics, number 166. My name is Walter Tangarife. I work at Loyola University, Chicago, and I will be the host today. And today it's a pleasure to introduce Dr. Rodolfo Capdevilla, who is a postdoctoral researcher at Fermilab near Chicago, Illinois. Rodolfo got his PhD at the University of Notre Dame in Indiana, and then after that, he was a joint postdoc between the University of Toronto and Perimeter Institute before moving to Fermilab. And today, he will share his work with us on muon colliders and the prospects of detecting electroweak interacting dark matter. Thank you for joining us, Rodolfo. Before I give you the floor, I want to invite you all to post your questions in the chat of our YouTube channel. Please subscribe to the YouTube channel and to all the social networks like X or Twitter, Facebook, and to our Google Groups mailing list so that you are posted on the upcoming webinars. All right, so thank you, Rodolfo, and please take it away.
Thank you very much. I guess I should share the screen. Okay. So, oopsie. So hello, everyone. Thanks a lot for tuning in, coming to see my talk. Thank you a lot to the organizers for considering me to give this talk. I must say that my collaborators, they are amazing people that have been doing a lot of this work for longer than myself. They could give a much better talk. They are amazing. So I'm gonna be sharing with you the summary of these two papers on electroweak interacting dark matter. So let's see. In the context of muon colliders. So I'm gonna give a brief introduction about future colliders, the questions that we have, what do we want to do, the status of the muon collider, for example, in case you haven't been following what's happening with the muon collider. Then I'm going to talk about these models, these electroweak interacting dark matter models. They are highly motivated for many reasons, I'm going to tell you. And then how we have been looking into these models, at colliders, including hadron and muon colliders, and then the results. So when we talk about future colliders, right, it's good to remind ourselves of this big picture questions that we have, right? So, for example, before the LXC, so we had these questions of what is the origin of mass, unification, flavor. So questions that we thought back then, they were this is a really important question. We need to go there and see what are the answers, right? So in case of the origin of mass, we had the Higgs as a very strong candidate. And we kind of have a nullus theorem, right? In the words of Chris Quigg, if we either find the Higgs boson or something very much like it, and also looking at this partial wave unitarity, we knew something was if there's no Higgs, something is going on at the TeV-scale. So that was very nice. Yeah. So now we found the Higgs, but that just opened up many more questions, right? So we have a description of the electroweak symmetry breaking at the level of Ginsburg-Landau, where a potential does this, but we don't have a macroscopic description at the level of BCS theory, right? So we have many candidates for what this macroscopic theory is, and we have ideas that this might show up at the 10 TeV scale. So then when in the discussion for future colliders, either leptonic or hadronic colliders, it always comes these two big pillars, right? So we want to do precision, we're going to measure the parameters of the standard model to highest possible precision so we can better understand the Higgs potential, the questions with the electroweak symmetry breaking and so on. But we also want to go to terra incognita. So we want to see what's out there in the highest energy, based on motivations that we have, like the picture of unification, flavor, dark matter, baryogenesis, but also things that we have no idea. Nature might surprise us in beautiful ways, right? So then, if you come now to muon collider literature, the recent literature, you're gonna see things like this, where the muon collider is a very good vector boson collider. Via vector boson, you produce many Higgses. So for example, just from WW fusion into one Higgs, you can see that a 10 TeV collider will produce, so we have picobarn cross sections with a spectral luminosity of 10 inverse attobarn. So we're talking about 10 millions of Higgses just in that channel. And that's very good, because then that allows you to measure the coupling between the Higgs and the W boson at levels much better than even a program like the FCC, EE, and HH, right? So in this, if you're not familiar with this, when I say FCC, HH, I'm going to be referring to a 100 TeV proton collider. Okay. And then, so other things you see is that, for example, the coupling with the Z, then the muon collider cannot do better than this program, for example. So in a sense, it's complementary. Right? And then for DSM models, you can find this literature on your favorite super partners, states that are related with compositeness, or even higher dimensional operators that come from this and can be constrained and better probed at the muon collider than other options. For example, I'm calling it Higgs portal. This is the scalar that mixes with Higgs. So this can give you things like, it can make the electroweak phase transition strong first order, for example. This could also be portal between us and dark matter. So this scalar is well regarded as a motivation for new physics. And you can see places in the parameter space of the mass and mixing where the muon collider could do better than other options. But then again, it's sort of complementary, right? For the higher masses, then an FCCHH could do better. Okay? Heavy neutral leptons that are related to, could be related to leptogenesis and neutrino mass and all that. So the muon collider could be probing higher masses that other machines couldn't do. Yeah. So, but before jumping into these dark matter models that I'm going to tell you about, I'm going to tell you a little bit about the status of the muon colliders, in case you haven't been to the muon collider workshops, right? Okay. So ideally, so we like circular colliders because they are multipass, right? You put the bunches into a ring, they pass through each other multiple times. So this way you gain in your recycle beam, you gain in luminosity, you gain in power, also you save power. And we like lepton colliders because then all the center mass energy is available to produce new states, as opposed to proton colliders where, you know, the partons only carry a fraction of the energy. And then lepton colliders are also very clean, yeah? So the ideal machine will be a super duper powerful electron collider. But then electrons have the problem that if you put that in a ring, they are gonna radiate, they Bremsstrahlung all the energy. So at some point, the power you put in, it just goes away. So that's why we do protons when it comes to the largest energies. Yeah. There's the concept of a linear collider where now you can collide leptons. So you gain a little bit of this, like 0.2 and 0.3 is center mass, you get in clean environment. But then they're not multipass, right? So then they cost a lot in terms of power. Yeah. So the muon collider is now it's posing itself, right? It's emerging as an option where you can do all these three. You can combine the beauty of having a ring, it's a lepton, so it gives you the center mass and it gives you a clean environment, relatively. But also you see things like this, that in terms of cost, power consumption, years to first physics. This is a report made by these people during the SNOMAS. These are accelerator experts. So there are other items in which the muon collider also looks appealing, right? In particular, the size, the fact that you need a ring much smaller than SSCHH. People are excited because now you can fit this machine at Fermilab. So you can bring the energy frontier back to the US, for example. So there are many challenges, of course. In this column here, you see R&D, research and development. And some of those challenges has to do with, for example, the cooling, right? When you produce muons, you smash protons into a target. And then these muons, they come from the decay of ions and all this. But so they are produced with a broad phase space. You need to make them pass through absorbers that absorb some momentum, and then you accelerate them so that they don't lose the boost. You want to maintain your muons boosted so they live long enough for you to do physics with them. Right? So then this was an amazing result from the mice collaboration in 2020. That's actually one of the things that got me really excited about this, where they passed a muon bunch through one absorber, and see this is the phase space. This is momentum and space, a spread of the bunch. And then to the left, you see what happens when it passes the absorber. The phase space starts shrinking. So they did, order 10% cooling, and now we need orders of magnitude cooling. So that's why we need a lot of research and development, because so far they have just worked with one absorber, but we need to put many absorbers in line, and we need to then assemble this arrange where you have RF cavities and magnets, and it's not trivial. This is an engineering problem of assembling all this together and see if it works. And it gets more and more challenging as you cool the beam more and more, because then you require stronger magnets and all this. So it's a very big challenge. Yeah. Another challenge is muons are they do decay in flight, and these decay products, they're gonna hit components in the tunnel, in the detector itself, and then create a shower of particles. So then, in a sense, it's not very clean, but people are studying it. So you see, for example, this is the time of the bunch crossing is t = 0. Get particles arriving before and after. A lot of photons, a lot of neutrons, electrons. Good thing is that these particles are kind of soft, as you can see here, right? We're talking about 0.2 GeV, 3, and so on. Yeah, so people are working on this these days. So talking about muon colliders for Fermilab is like when you have an idea and you say, well, I'm busy right now, I'm gonna put this idea in the freezer. So back in the days, we're talking 1997, there was a huge excitement at Fermilab, like a lot of people working on this. Even early 2000s, as you can see. So they created it's in the US, they created the MAP collaboration, Muon Accelerator Program. If you look it into Inspire, it says that it's still running. I didn't know. All right. So now the US is excited about this again, and wait, yeah. So they did some work on this beam-induced background, on beam dynamics, detector, and all this. And what happened over the last few years is that Europe revived this idea, because the idea pretty much died in 2013, 10 years ago, after the previous P5 process. For those of you who don't know, P5 is sort of it's a panel that make recommendations to the funding agencies in the United States. And you know, back in the days, they didn't recommend the muon collider, so it sort of died in the US. But since a little before 2020, in people at CERN and other places in Europe, they started reviving these ideas, seeing what the MAP collaboration did. In 2020, they created the International Muon Collider Collaboration, IMCC. And over the last few years, these people have been making studies in the different aspects of the Muon Collider. So cooling, detector, beam dynamics, beam-induced background, all this. We're getting ready for the next European strategy. And then after this, there's a period of 10 years each, 10 years each, where these demonstrators in different aspects, what I told you about, for example, the assembling all these units into the cooling, all this, things like that, things like target, right? You want to be able to, when you smash the protons, to maximize the muon production, even at the level of the target and all this. So the idea is that in those 10 years, some of these demonstrators will run and prove that we can do this, we can do the muon collider. Okay, so much for that. Let's jump into the physics models. So as a sub pillars of this BSM, unknown, and energy frontier, you can find your favorite motivation for it, between mass and so on. These electroweak interacting dark matters, in a sense, they appear in this multiple of these pillars. They are, of course, related with dark matter, of course, but also the models, the construction that appear here, they appear in supersymmetry models like a split SUSY, for example. Yeah, so that's how I'm connecting it with the hierarchy problem and the unification. So these models can be realized without supersymmetry. They are very simple, but they sort of show up in supersymmetric construction, which is very nice. And so the idea is very simple. You just, to the standard model, you add an electroweak multiplet, right? This could be a doublet, a triplet, fiveplet, whatever. And you make sure that there is a neutral component in the multiplet. And that is going to play the role of the dark matter. Yeah. So for the experts in the audience, so this is not totally accurate. You need to make this interaction inelastic. So actually, instead of having one Dirac state, you have two states that mix with a tiny splitting between them. So the interaction is actually inelastic. If it was like this, it would have been discovered by direct detection experiments. Yeah. So then in these models, all this early universe story is there. So this is a very so things get complicated very quickly. You need to compute this annihilation in the early universe into standard model states. And as you probably know from thermal freeze out, so you have that matter in the early universe in equilibrium. And then at some point, so it starts falling in the Boltzmann suppression here. So it means that you're annihilating that matter. And then at some point it falls out of equilibrium. And this is the relic density that we measure today. So if your annihilation cross-section is very big, you end up annihilating too much dark matter, and you end up with very little number density, which means that dark matter needs to be heavy to accommodate the density that we measure today. So in these models, the annihilation goes with the size of the multiplet, right? So the larger the multiplet, the more they annihilate. And then the heavier they need to be in order to give you the relic abundance. So for doublets, we're talking about things like around TeV, triplets, 2, 3 TeV, fiveplets, 10, 14-ish TeV, and so on. Yep. So then you have plots like this where, as a function of the mass, you can know how much of the relic abundance they give you, right? So this line over here, they give you 100%. So I'm going to be talking later about a 100% Wino. So that would be a triplet with a mass of around 2.7 that gives you 100% of the dark matter. But then if I say a 10% Wino, I'm talking about a triplet with a mass of about 800 GeV that give you 10% of the relic abundance. Okay. Okay. So projections. So this, as I told you, it gets complicated very quickly. In order to compute direct detection cross sections, you have to compute all these loops. There are some accidental cancellations for the doublet, the Xeno, that make this quite challenging. But then when you look at the projections for direct detection, you see things, very nice things like this, where all of these models, these triplets, 6 tuplets, 8 tuplets, and so on, that they will be so future direct detection experiments could probe these scenarios. And then you see these nightmare scenarios like the doublet, the Xeno, or the 5-plet that fall beyond these projections. Yeah? So if these are dark matter, they are accumulated in the galaxy, so they can annihilate and give you petaphotons, for example. So there are you can find papers where the Xeno, sorry, for example, the Wino is already ruled out by indirect detection from the center of the galaxy. So this point here will be the annihilation cross section for the Wino, for the triplet, and this is how far the bounds go. So you would say it's ruled out. But then in this most recent paper, by just like a week ago, you see, for example, for the Xeno, what are these? These are projections for CTA, where depending on the assumption about the density profile of dark matter in the center of the galaxy, you have different reach, right? So this is the famous NFW profile, as you can see. For the Xeno, you will reach around 2 sigma, right? So for other assumptions, for other profiles, you might see the 5 sigma. But yeah. So now in colliders, there is something beautiful about these models that so the charged component members of the multiplet and the neutral members of the multiplet, the dark matter, they have a splitting. So if you make no particular assumptions about other interactions of this particle, there's a natural, very tiny splitting between these two. It comes from loops of photons, just the electromagnetic self-energy. And then this gap is of the order of, for example, here for the Xeno, the doublet, we're talking about 0.3 GeV, whereas the mass, if you remember, we're talking about TeV masses, right? Very small splittings, TeV masses. That gives you that, as a feature, as a nice feature of the models, that these particles are long-lived. So we're talking about 1/10 of millimeters for the lifetime, right? I feel like I'm going very fast, but I'm not sure. Let's see how it goes. So at the colliders, you can look for either directly producing the dark matter candidates, which will give you missing energies, searches for missing energy. You could also produce now this heavier charge state, and which is gonna go through the detector for a little bit and then decay, giving you a disappearing track. Okay. So I like quoting this pioneer work by Matt and Lian Tao, where so they taught us how for the Xeno, the doublet, and the triplet, a 100 TeV proton collider could, for example, in the case of the Wino, could go to 5 sigma within uncertainties to what we call the thermal target. So when I say thermal target, it means the mass for which this particle give you 100% of dark matter. Yeah? So you're familiar with the jargon. Whereas for the Xeno, reaching the thermal target is quite challenging. So you already saw it, right? Direct detection, indirect detection, colliders. It's always very challenging to detect the xenon. Then there's this work by Tao Han, Shen Liu, Len Tao, and collaborators, where they show the different muon colliders and different of these multiplets, different searches for them with two muons, one muon, one photon, and so on. They show so they made this estimates with fast simulation of 1 and 2 disappearing tracks. Right? What happens if you produce 1 or 2 of the charge particles, and they give you 1 or 2 disappearing tracks with an extra photon in the event. So the estimates look quite good. As you can see, between 6 to 10 TeV muon collider could potentially get the thermal xeno. That's a very exciting result. And then you see other projections for other multiplets, like 5-plets, triplets, and different assumptions for the muon collider as well. And this all looked very nice. So then, from this point, what we did was to add to this analysis, in particular the xeno and the Wino, detector simulation. So let's see if these fast simulation results, how do they look if now you take into account more rigorous treatment of the beam-induced background, right? Because we're looking at disappearing tracks. The tracker is our detector. And then, as you saw from the beam-induced background, you're going to get many tracks. So background could be potentially a killer for this. Right? So we use detector design borrowed from Click. This is back in 2020. There are new designs around. You ask people. So here you have the Muon system, colorimeters, tracker, and this is going to be our sub-detector, the vertex detector. So this looks like this. Look at this. So these are the nozzles, right? So the nozzles are like cones of tungsten, whose job is to shield a lot of this beam-induced background, right, coming from before the bunch enters the detector, right? Oh, I guess even also when it enters. So this, okay, it's a bummer that you lose some angular coverage in your physics. This is about 10 degrees in this design. And then these 4 layers over here are this now in the, looking at it in the transfer direction, this would be 1, 2, 3, 4 layers. These are double layers. And the fact that they are double layers was important for this study. I'm going to show you how. And we're talking about distances of 50 to 100 millimeters. Right? So the beam-induced background. So these are a bunch of soft particles. They arrive late. They don't not necessarily arrive at the bunch crossing, as I showed you before. And they are mostly forward. Right? They come from the decay of the muon. They don't come from like hard collisions in the center, as opposed to our signal. Right? This is coming from a hard collision that gives you this charged particle. So then you'll see you need to define a time window where you want to look for this for your signal. And also you need to look into, this is what I told you about the double layers. So the double layers help you to look at the angular direction of the tracks. And with a certain angular cut, we're able to eliminate a lot of the background. Right? So you see things like this, right? You go from 10 to the 5 down to 10 to the 3 and so on. So this the acceptance volume, sort of like the signal region is is constrained in a sense after the second double layer. Right? So you want to look at things after the second double layer. This is mostly because of the beam-induced background before that is quite overwhelming. And then we went up to the like this is the last double layer and the beginning of the inner tracker over here. Okay. As you can see, when you look at the projection, this is the mass of the charged particle that you're producing. This is the Higgsino, the doublet assumption. This is the Wino, and what you see in this plot is the regional parameter space in the lifetime and mass that you can cover with this particular search. Yeah. So then, if the lifetime is long enough, your particle is going to make it easily here, and you're going to have a pretty good probability of reconstructing this signal. This is what this axis is indicating. Yeah. So you see this dotted line over here represents indicates the lifetime of the triplet, the Wino. So then what you would see to set bounds is that the point where these two lines intersect is more or less how far you can go and looking for these particles. So these colors over here are different options, like the high Lumi LXC, then the 3 TeV Muon collider could start covering a little bit of this parameter space. Yeah. So the situation when we put out this paper 2021 was this: both FCCHH and 10 TeV Muon collider can discover the thermal window, the triplet, right, with a 2.7 TeV mass. So the lifetime is long enough that these states, they give you a nice disappearance track. Yeah. But then the Xeno also, very challenging. The lifetime is not long enough. The cross section is also not as high because it's a doublet. The window is a triplet, gives you more cross section, more events. Yeah. So then you see the threat. You see you see what's happening, right? So either direct detection, the Xeno is a nightmare. For indirect detection, depending on the subject, but the Xeno is going to be challenging. And then colliders, the Xeno also, again, challenging. So that's why we started this business over here of now, instead of looking for the disappearing track, we are looking for what we're calling the soft track, right? So look at this. Because of the small gap between the charged particle and the neutral particle, so you can compute the decay channels. If we are talking about the pure Higgsino case, the 0.3 GeV-ish splitting that I told you about, we're talking about a 90% branching ratio into pions, and then other 10-ish% to electrons and muons, right? So either of these particles you get, we're calling it a soft track. You know? So now, to start understanding the kind of signal that we're after, let's do this tiny cartoon exercise. Yeah? So let's say you produce the Xenos at threshold, the charge component at threshold. They don't move very much. Then they decay. So they're going to decay into the dark matter and the soft track. But then the momentum of the soft track, there isn't much momentum available for the soft track, right? So remember, the splitting is about 0.3. So you don't expect in PT to find events beyond the splitting, right? The cross-section should sort of die here. Now you produce the Xenos with some boost. Because of this boost, now there is a little bit of energy for your soft tracks. So you developed sort of like a tail in PT. Now, to put numbers, I'm in this study, we're focusing on the thermal Xeno for the reasons that I just told you, right? It seems to be the most challenging, a very challenging case. So this is a state of a 1.1 TeV mass, 0.3 GeV in mass splitting. So then for the 3 TeV collider, what are we talking about? We're talking about a PT for the soft track around this is the 0.3 point. So not much beyond 0.75, right? So your signal is all within 0.2 for us and 0.75 in GeV. This is a very, very, very challenging signal to look for. All right, now let's think about the rates. So for the Xeno, we're talking about at the 3 TeV collider, 10 femtobarns ish, right? So that's 10,000 events, just as a first glance. But then when you produce the Chargino, you not always get 2 soft tracks, right? Because your Xeno could then give you a soft track in the nozzle, so out of the acceptance. You could get 0 soft tracks from then 1 or 2. So the first exercise we did was to explore all these different signal regions, how things look. Like if you have only 1 soft track and 0 photons, 1 soft track, 1 photon, 2 soft track, 0 photon, 2 soft track, 1 photon, so on. So for the good one, the good signal region, the one that like the golden one, we're talking about order 1,000 events ish. So we're after 1,000 events in the 0.2 to 0.75 GeV PT range. Then the challenges. So the beam-induced background gives you 2 main challenges. It gives you a lot of noise. So hits in the tracker that then your tracking algorithm is gonna get confused and not being able to reconstruct your soft track. So look at these numbers. This is for muons, which are supposed to be nice and easy, and this is for 1 GeV. So you lose efficiency, the ability of reconstruct the tracks as you move towards the end caps. So the central region of the barrel is quite good, but again, these are muons, which are nice, and this is 1 GeV. So what we're looking for is below 1 GeV and pions, which are not as easy than electrons also. Our study uses beam-induced background data from the MAP collaboration. So in a sense, it's conservative because this was produced for a 1.5 TeV center mass collision. If you produce this data for higher energies, it's more forward. So the beam-induced background tend to be more forward. So in principle, it's better. It's going to be better once we have the new beam-induced background data, right? So then, your experimental colleague there runs the detector simulation, does the magic, and give you this. So the probabilities for being able to reconstruct these soft tracks in a given momentum and in a given angular region. Yeah, so we had to require an extra photon. I'm gonna tell you why. And this is the signal region that we are working with. Right. The beam-induced background also gives you fake tracks. It doesn't only spoil your ability to reconstruct the actual tracks, but also give you fake tracks. Lucky for us, well, doesn't always happen that nature is nice with you. So as I told you, the beam-induced background tracks, they are very forward, whereas our signal is very central, right? So this is the reason why we're focusing on this 60 to 100 degree in polar angle. As you can see here, you lose the efficiency very quickly as you move out of this angular region, right? Then there is, of course, real processes in the standard model that give you soft tracks. You can produce 2 leptons, 2 taus, 2 strongly interacting particles that then decay and give you these soft tracks. So we computed all this, and I can tell you right away. So if you look at the signal region without photon, the background is orders of magnitude above the signal. Yeah. This is why we require the extra photon, because now as you push the momentum, the PT of the extra photon, in order to balance that, then the soft tracks from this other standard model processes, they start going out of the acceptance. So you get rid of a lot of the background with that. Right. So then this is how the signal looks. So this beautiful Higgsino signal here, you reach the 5 sigma at the 3 TeV collider, which is amazing. So the Muon collider has one possibility is to have the 3 TeV and then the 10 TeV. So we're saying the 3 TeV is not just a stage. You can already start discovering these very highly motivated models. But it's not just that. It's not just the Higgsino, right? You can see plots like this. This is probably out of date. I should look for the most outdated version of this. But you can see, for example, like this, as I told you, for the indirect detection, they claim we know the triplet is already rolled out. But that's making an assumption about not only the density profile of dark matter, but also the amount of dark matter that the triplet accounts for. Right? So if the triplet accounts for 10% of the dark matter, as you can see, its mass is around 800, and it evades these constraints. Probably with the most recent constraints, this line is going to go way below. So then the situation is this, that indirect detection is now covering these models from above, and colliders like the LXC, they are coming from below. Okay? There's a middle point here where then the Muon collider can fill in, right? So that's why in our paper, you're going to see these boxes over here. So the 10% we know, the 1% 5-plet, and the 100% Higgsino. Right? Those are the things that we can cover. So the situation for the Higgsino now in the context of Muon collider, you see even the 3 TeV, we can go up to the thermal target. But also the 10 TeV with, so like Federico and some colleagues, they have updated these studies of disappearing tracks and found ways to improve these results. So basically to state the legacy of this work, if I die tomorrow, you can remember me as the guy who told us how the Muon collider can discover these doublet, triplet, 5-plet models. Starting at 3 TeV, we can this solid line over here is the 5 sigma discovery. The bottom is for soft tracks. The upper belly here is for disappearing tracks, and then the dash is the 2 sigmas. So at 3 TeV, you can start looking into Higginos that cover fractions of the dark matter up to 100% of dark matter. In the case of triplets, you go from 10% up to 20%, and 20 few if you include the 2 sigma reach. And then for 5-plets, order 1%, right? So if the 5-plet exists in nature and it accounts for 1% of dark matter, that state is going to show up in these searches. Okay? Then for the 10 TeV collider, now because we already covered the Higgsino here and the other lifetimes are above. So we haven't extended the soft track search for the 10 TeV collider. There are many technical difficulties there. We might do it, but like already at this point, you will cover the 100% Higgsino hypothesis at the 3 TeV, and then for the 10 TeV, you'll go and start probing 30, 50, 100% Wino, and as well as 5 and 10, even 15% of the 5-plet. Right? So that's basically my story. So you saw the results that I showed you for indirect detection, how they claim they can cover doublets, triplets, and so on. But what I'm saying is this: if they find a 2, 3 sigma, 4 sigma evidence for Higginos, for example, that would be a very strong motivation to go for the Muon collider. I would say that this is very good. That it's not a problem. We can build CTA and we'll find a 4 sigma consistent anomaly consistent with Higgino, and then we'll discover that the Muon collider. That's the story. And well, thank you so much for listening.
Thank you very much, Rodolfo, and thank you all for listening. So now it's the time for questions. Please remember that if you have a question for Rodolfo, you can write it in the chat in YouTube, and they will be happy to read these questions to the speaker. While you do that, I'm going to open the floor to see if anyone who is in the Zoom meeting has a question for Rodolfo. Joel?
Yes, thank you for the talk. It was very nice. I was wondering, so regarding the Higgsino's, right? You say, okay, they're too short-lived to make them sensitive to make searches for disappearing tracks sensitive to the signal. So then in that case, wouldn't it be also possible to probe this scenario with searches for missing energy?
Yeah. These people, they did it.
How would they compare?
Let's take a look. Here, these people do it. So let me see. You have mono mu, mono gamma. As you can see, it seems like so mono mu searches. If you have also 6 to 10 TeV collider, you might be able to go to the thermal target. So I'm not fully, so dimuon plus missing energy. And then monomuon here. I guess dimuon plus missing energy doesn't show up. And then this color here is monomuon. So yeah, there seem to be other techniques that could cover this at in the range of 6 to 10 TeV collider. Well, I would say more than. No, you gotta be 10 and a little above because this is already blue. This is 14. So 10 will be here. So above, you will need above 10 TeV maybe, if I'm reading this correctly. Yeah.
So the point is that you can probe you can probe the scenario with just 3 TeV. Well, the other searches would require larger energies.
Yeah, exactly.
Okay, great. And could you please? I'm sorry because I didn't understand what was the role of the photon in the part of the soft.
Yeah, because
I didn't really understand why it was so important.
Yeah, because like these numbers that I told you about, the rates, we're expecting 1,000 events in this signal region. Then there are different signal regions. You could have 2 soft tracks and 0 photon, 1 and 1 and so on. And these are numbers for this 2 soft track and 0 photon signal region, and the black is the signal, okay? The blue is just the tau. Just you produce 2 taus with something else, and the taus give you soft tracks, and just that, the background is already orders of magnitude, like 3 orders of magnitude above, right? So now, when you require the extra photon, in order to balance the PT of the photon, these tau soft tracks they start becoming harder and harder. So they go above here. They merge into higher PT bins. So then with only 10 GeV, you already start making these numbers comparable. But in order to make it this efficient, we realized that 40 is the best option. So you can also see it here. Like the photon PT is pushing all these events into into this region. Yeah.
So in the case of the taus, the photon comes from both initial state radiation and say final state radiation from the tau, while in your case with the Higgsino's, no, but hang a second, the Higgsino can also be charged, no? So it can also, but I guess that the radiation emitted by the Higgsino is not the same.
Yeah. So, but the bottom line is that these are very heavy. So even you can afford emitting a 40 GeV photon and not really be affected by
I got
that.
it.
So, yeah.
Super. Yeah. Great. Okay. Thank you very much. It's much clearer now.
Yeah. Thanks for the questions.
All right, any other question? Roberto?
Yes, very nice the talk, Rodolfo. I like it a lot. So I was wondering, is any potentiality in this kind of collider to analyze kind of rare muon decays like the lepton flavor violation cases? I mean, I know that is very rare, the event. So I don't know if with this capacity of producing so much muons for the colliding, maybe some of them can decay producing this rare event and analyze it or after that. I don't know. Kind of.
Absolutely. I should have put at least one plot showing a flavor. You can find more in this. This is called the Muon Collider Hunter's Guide, something like that. This paper over here. You see cases where some higher dimensional operators involving maybe tau and 3 muons, if I remember correctly, bounds that are comparable with flavor factories, even Bell 2 type of sensitivity. And I remember. So Dario Butazzo, he's spoken about this in the Muon Collider meetings, where so the idea is that so here you have an operator that's suppressed by some scale, but when you compute the cross section, this becomes a ratio of the energy and the high scale. So by going to higher energies, even though you're not as sensitive as a factory, but you start gaining in that sense, because now the ratio of energy over the higher dimensional operator is not as bad. Yeah. So here you can find more on that.
Okay, thank you.
Yeah, very good, very good. I'm gonna add one plot about flavor. That's very good. Yeah.
All right, I don't see any questions on YouTube. There is Adrian says, thank you for the nice talk, and a happy smiley face. All right. Well, if there are no more questions in the room. Oh, yeah, Joel.
Sorry, one more. No, I was wondering about the beam-induced background on the disappearing track search, right? Because that's I was surprised about this, because I was reading a bit about this on the LHC, that it can affect searches for long-lived particles that leave no tracks but deposit their energy in the calorimeter, right? So my idea of the beam-induced background was that this would, you would have a very soft tracks, right? But have you could have larger energy deposits on the calorimeter. Well, here you have the opposite, right? You have like a hard track, right? And then you have no energy deposit or very few energy deposits on the calorimeter. So is this due to a different nature of beam-induced background from the Muon collider, or maybe I just learned about a particular type of beam-induced background, or maybe there are more. But still, I was surprised that when you have a track, usually you can point them towards the primary vertex, and I'm also surprised that you could have these things that come from the beam and at the same time be a background and reconstruct a vertex some sort.
Yeah, because they're gonna, so imagine a lot of forward tracks overlay on top of each other. So you could identify one hit from one track and then another hit from a different one, and then your tracking algorithm is reconstructing as a one hit that is not.
Okay.
Because it's overwhelming. It's so many events.
I see.
Yeah, I think this is what this plot over here is trying to say, but I didn't explain enough. So
well,
we're talking about hundreds of thousands of events, and that's why. So when we apply the time window, we're reducing it by about 1 order of magnitude, and then the directionality then helps. So imagine this is the double layer, you want some angle between the heat in the first layer and the second layer, the angle. That's what we're doing over here. And that angle then kills, almost a couple of orders of magnitude. Yeah, so they, order 3 orders of magnitude in background rejection when you do this different cuts. But no, that's a very good point, actually. At some point, we were afraid of in the soft track analysis, that you have these taus giving you so many soft tracks that maybe the BIB-induced background could then, random hits from the BIB-induced background could, pile up in the ecal and give you a fake photon. Give you a fake photon that now you pair with the taus, and then you have a fake signal. So that's why we do full simulation, right? So our colleague, Federico Meloni, he checked, and that's also why the 40 GeV cut on the PT of the photon, that it helps also because of that reason. Yeah, that's a very good point. Yeah.
I see.
Yeah,
okay. Oh no, it's interesting.
Yeah. So I show you that already with 10, we're doing good in terms of making signal and background numbers similar. But no. There's also the ecal problem. So that's why we had to go all the way to 40. Yeah.
At the LHC, they used machine learning for that to reconstruct the shape of the jets coming from their signal and from the beep, and that's how they reduced it.
Yeah.
But I guess this is better. This is simpler. Just put a cut of the photo.
Yeah.
Okay. Thank you very much.
All these searches are going to be improved. We're doing cut and count. We're doing simple things.
Yeah.
By the time we have this collider, these searches will be much fancier.
And what was the expected timeline for you put it, but what was the expected starting time? Could you please remind me?
Okay, so this is the optimistic. So only technically limited. So by 2045 and 50, the machine could be running. There's the money.
I'm gonna be too old for that. I'll be writing books by then.
Yeah. No, but take into account that this is only technically limited. Then there is politics. There's
yeah.
So
Let's
it
not
could
go
go
into
to
that.
60, 70. Who knows?
Okay, so my students will get into that. Good.
Yeah.
Okay,
all right.
great.
Excellent. Thank you for your questions. Andres Felipe Rivera also says thank you for the talk on YouTube. To all of you who are watching the talk on YouTube or who will watch the talk later, please remember to subscribe to all of our social networks, Twitter or X, Facebook. Go to our page in WordPress to subscribe to the mailing list through Google so that you are posted on the next season of talks. And please remember to subscribe to this channel. We will have an upcoming webinar in 2 weeks, so be looking out for the announcements. And thank you again, Rodolfo, for this very nice talk. Hopefully we'll have in a few decades a Muon collider and we'll find Electroweak Interacting Dark Matter. And to all of you who joined us, thank you very much, and we'll see you later. Have a nice rest of the week.
Bye-bye.